Hello, dears. Welcome to the Science for Sleep channel. In the darkest boundaries of the solar system, far beyond the asteroid belt, there exists a giant sentinel that endures with silent yet absolute power. This place is a foreign world where never-ending colossal storms reign, deadly radiation flows like invisible rivers, and breathtaking beauty always stands alongside danger. Jupiter is not merely a planet. It has such immense mass that it affects everything around it, even the sun that gives it life, in a tangible way. Suspended between the orbits of Mars and Saturn, in the dim depths of space, this gas giant is not only the greatest architect of our system, but also its most mysterious guardian. The secrets hidden within its clouds hold key clues not only about a single planet, but about how our entire star system was formed. If calm journeys among these silent giants in the universe bring peace to your mind, and if you haven't already, you might consider subscribing to our channel and liking tonight's journey. Your presence allows these deep space explorations to reach more curious souls. Now, sit back, free your mind, and let's pass together through this door leading to the world of giants. We begin. To truly understand Jupiter, we must first liberate our sense of scale from earthly measurements and elevate it to a cosmic level. Because it has approximately 2.5 times the mass of all the other planets in the solar system combined. If we place the entire system on a massive scale, putting the sun on one side and everything else on the other, nearly all of the mass on the second side would be Jupiter. While the sun alone carries 99% of the system's mass, Jupiter is the undisputed ruler of that tiny remaining 1%. This extraordinary mass gives it not only the identity of a planet, but also the potential to have been a failed star. Structurally, Jupiter resembles our glowing star far more than the rocky worlds we inhabit. The deep layers of its atmosphere are filled with hydrogen and helium, the universe's most fundamental building blocks. The frequently asked, childlike question, if we threw a match into Jupiter, would it ignite? Is, in fact, a sorrowful sign showing how close it came to becoming a star, yet it could not cross that final threshold. But stars do not burn like this. To ignite, they do not need oxygen. They require an incredible pressure in their cores, capable of initiating nuclear fusion. If Jupiter were about 75 times heavier than its current mass, it could have ignited under its own gravity and shone in our sky like a second Sunday. However, it completed its growth without reaching this threshold and remained a cold sun, shining only with its internal heat in eternal darkness. This massive mass creates such a deep warp in the fabric of space-time that the relationship between Jupiter and the Sun is far more complex than a simple one revolving around the other. We generally think of small bodies orbiting larger ones, yet gravity is a mutual interaction. Jupiter is so massive that the common center of mass between it and the Sun, the barycenter, is not within the Sun's core, but just outside the star's surface, in space. Technically, this means Jupiter does not revolve exactly around the center of the Sunday. The two giants perform a mutual waltz in the dark at the end of an invisible rope. Even the Sun cannot remain indifferent to Jupiter's majestic weight and sways slightly in space, adjusting to its rhythm. When viewed from Earth, this giant, shining as one of the brightest objects in the night sky, is actually located about 778 million kilometers away from us. At this distance, where even sunlight takes a long time to travel, Jupiter governs its own miniature solar system. The dozens of moons orbiting it, the captured asteroids, and its extremely powerful magnetic field clearly show that it is not just a planet, but a center of power in its own right. This enormous sphere, approximately 11 times the diameter of Earth, rotates so quickly around its axis that its equator is noticeably bulged compared to the poles. This rapid rotation is the primary engine behind its iconic bands in the atmosphere, the ever-raging giant storms, and the chaotic yet mesmerizing face of the planet. Jupiter is constantly in motion like a sleepless giant. It continuously changes and whispers cosmic songs into the depths of space that we are only just beginning to hear. Most of us, when imagining planets, think of them only in terms of the colors visible to the human eye. Saturn's pale golden tones, Neptune's deep ocean blue, or Jupiter's iconic red and white stripes are what stick in our minds. Yet observing the universe with only our eyes is like looking at the cover illustrations of a vast library. The real story lies between the pages, in the wavelengths of light that are invisible to us. For scientists, looking at Jupiter does not only mean observing its outward appearance. It also means reading the planet's chemical soul through infrared and ultraviolet wavelengths. These different perspectives transform the familiar giant gas mass into a completely alien, almost otherworldly realm that feels like it belongs to a universe of its own. In essence, each observation peels back a layer of mystery, revealing the subtle complexity hidden beneath the colorful clouds. As we approach Jupiter, the enormous cloud layer we encounter is composed not of water vapor like on Earth, but largely of ammonia ice. These clouds form only a thin shell in the planet's atmosphere, roughly 50 kilometers thick. Yet this delicate layer acts as an elegant curtain, concealing the deep darkness and chaos lying beneath. Viewed in visible light, it becomes apparent that the clouds drift at different altitudes. The darker and narrower bands are often merely the shadows cast downward by high-altitude, light-colored clouds. The bright, snow-white structures at the uppermost layers of the atmosphere rise like mountain peaks, surveying the world below from above. But why does Jupiter possess such a mesmerizing variety of colors? Why does the planet display a rich palette ranging from brick red to orange and countless shades of brown, instead of being clothed in white tones alone? The answer lies in mysterious chemical compounds called chromophores that are transported upward from the planet's depths. These substances rise from Jupiter's hot inner layers to reach the upper atmosphere. There, they encounter ultraviolet rays from the sunday. Just as old photographic film darkens when exposed to light, these compounds interact with sunlight, darken, and give the planet its familiar, dramatic colors. This process resembles a continuous chemical dance. The materials rise, change color, and then descend again into the depths, disappearing from view, only to begin the cycle anew. This chemical ballet is accompanied by immense atmospheric motion. Winds sweep across the planet at breathtaking speeds, shaping the bands and storms that define Jupiter's face. The chromophores do not act in isolation. They move with the storms, riding the towering vortices and whirling currents, constantly reshaping the visual spectacle. Each cloud, each streak of color, is a living, dynamic painting, crafted by both chemistry and the raw energy of Jupiter's ever-moving atmosphere. However, When we close our eyes and look with our technological vision, that is, infrared sensors, a completely different landscape emerges. Infrared is the language of heat, and Jupiter speaks it extremely loudly. The planet emits far more energy back into space than it receives from the Sunday. This is because Jupiter has been gradually contracting since its formation, producing an enormous amount of heat in its core during this process. In infrared images, we see this internal heat rising from the depths of the planet as a glow seeping through the cloud layers. In regions where the cloud cover is thinner, heat can escape more easily into space, and these areas shine like bright beacons in infrared vision. This thermal perspective presents us with the opposite of what we are accustomed to seeing. High clouds that appear bright white in visible light trap internal heat due to their thick and cold structures. Therefore, they appear as dark and shadowy spots in infrared imagery. For example, Jupiter's most famous feature, the Great Red Spot, looks like a cold and dark shadow when examined in infrared. This is because it is a massive storm tower reaching high into the upper layers of the atmosphere, effectively concealing the heat beneath it. The extremely precise measurements of the Juno spacecraft, combined with these thermal maps, have revealed the three-dimensional nature of structures in Jupiter's polar regions. The enormous cyclones seen at the poles are not merely winds swirling at the surface. These structures are powerful heat engines extending deep into the planet. The centers of the storms are warmer than their surroundings and act as if they are windows opening from Jupiter's interior to the surface. Jupiter's atmosphere is not a place where gases are simply dragged along. It is a vast, dynamic laboratory where heat, chemistry, and light are in constant interaction and struggle. In addition, these thermal insights show us that the planet's hidden currents are in perpetual motion, driving both the visible cloud bands and the unseen flow beneath. Every storm, every swirl, and every heat plume contributes to a complex energy network that sustains Jupiter's ceaseless activity, revealing a world far richer than what our eyes alone can perceive. In this cosmic laboratory, events of unimaginable intensity by Earth standards occur every moment. Yet, when observed from afar, all this chaos appears on the surface, like a colorful, peaceful sphere spinning silently in the void of space. At the intersection of Jupiter's mesmerizing bands and complex belts lies the solar system's most iconic atmospheric feature, the Great Red Spot. This structure is far more than an ordinary storm. It resembles a massive, ever-rotating eye, seemingly etched onto the planet's surface. Its size is so immense that it could entirely encompass Earth. It has persisted for centuries. In fact, since Galileo first pointed his telescope at the sky, this storm may have continued to churn within Jupiter's atmosphere. However, even this ancient giant is not completely immune to the ravages of time. Observations reveal that the Great Red Spot has been slowly but steadily shrinking. It is as if the aging giant is gradually losing its strength. Nevertheless, its presence still remains the most striking evidence of the intensity and dynamism of Jupiter's atmosphere. The storm's color can vary from brick red to pale white tones. Its exact source is still not fully understood. However, the most compelling explanation relates to its altitude. The Great Red Spot rises far above the surrounding clouds. This exposes it more intensely to ultraviolet radiation from the Sunday. Chemicals transported from the planet's depths break down under this relentless radiation, producing the familiar deep red hue. The storm is so tall that it soars above other clouds, much like a lone mountain peak rising over a foggy sea. Yet, Jupiter's atmosphere is far more than a single storm. The planet resembles a living organism, continuously producing new formations. In recent times, the merger of 3 smaller storms gave rise to a new vortex called Red Spot Jr., or the Little Red Spot. This young storm managed to persist without being torn apart, while passing alongside its massive, elderly neighbor. Events like these clearly demonstrate that Jupiter is not a stagnant gas sphere. Its atmosphere is constantly reshaping itself, with storms forming, merging, and sometimes dissipating. These storms are transient structures emerging from chaos that can last for hundreds of years. So, what lies beneath all these storms? This question takes us on a mental journey toward the planet's core. Jupiter has no solid surface. It is a vast ocean of gas composed of roughly 90% hydrogen and 10% helium. As one descends, the weight and pressure of the overlying gas reach unimaginable levels. Under this pressure, hydrogen first becomes liquid and then transforms into a metallic form. Deep within the planet lies an exotic substance that cannot be replicated in any laboratory on Earth: liquid metallic hydrogen. This extraordinary ocean is compressed under Jupiter's immense gravity and moves along with the planet's dizzying rotation around its axis. Jupiter rotates so rapidly that a single day lasts only about 10 hours. This incredible speed flattens the planet and drives the metallic fluid as a massive dynamo. The internal motion in Jupiter's depths produces both the solar system's most powerful shield and, at the same time, its deadliest trap. This structure, called the magnetosphere, is Jupiter's magnetic field and is 14 times stronger than Earth's. Excluding the Sun's massive sunspots, it is the largest single structure in our solar system. If Jupiter's magnetic field were visible to the naked eye, it would appear as a colossal sphere covering an area far larger than the moon in the sky. This invisible shield captures charged particles from the Sun, accelerates them, and transforms them into lethal radiation belts orbiting the planet. Yet around this giant, there are not only storms and magnetic fields. While not as grand as Saturn, Jupiter also has its own rings. These rings are not made of ice. They consist of extremely fine dust particles flung off by meteoroids colliding with their moons. They are faint and dark, making them nearly impossible to observe from Earth. Nevertheless, they exist, wrapping around the planet's waist like a ghostly belt. Jupiter's pale rings and deadly radiation belts form an invisible cage that simultaneously protects and threatens its moons. The planet's gravity is so overwhelming that everything around it, asteroids, comets, and satellites, is forced to yield to its will. Now we are ready to trace the path of a cosmic disaster that unfolded in this giant's orbit. For Jupiter's history is written not only with creation, but also with destruction. The deep silence of the universe is often deceptive. When we gaze at the sky, we assume that stars and planets glide in endless tranquility and immutable order. Yet behind this serene facade lies a chaotic past filled with violent collisions and cosmic destruction. Remember the great asteroid impact on Earth millions of years ago that ended the reign of the dinosaurs. Humanity long assumed that such catastrophes belonged only to the distant past, confined to dusty pages of geology books. However, on a chilly March night in 1993, under the dome of the Palomar Observatory in California, this assumption proved fragile. Carolyn and Eugene Shoemaker, along with their colleague David Levy, aimed their telescope at the region of space containing Jupiter and encountered an extraordinarily strange sight. What they saw did not resemble a typical comet at all. It had neither a single bright nucleus nor a single trailing tail. Instead, it consisted of 21 separate pieces arranged in a line, like a necklace of pearls scattered across the darkness of space. This fragmented celestial body was named Shoemaker-Levy, 9 inches honor of its discoverers. As astronomers analyzed the data, they realized that what they were witnessing was more than an interesting comet. In fact, they were witnessing a turning point in the history of the solar system. The culprit of this fragmentation was clear: Jupiter. The king of planets generates such a powerful gravitational field that any object passing nearby has only 2 options: become a loyal satellite or be torn apart. Shoemaker-Levy 9 had deviated from its calm journey around the Sun years earlier, probably in the 1,960 seconds or 70 seconds, and had been captured by Jupiter's invisible gravitational net. Approaching this giant came at a heavy price. Jupiter's tidal forces were so immense that maintaining the comet's integrity was impossible. The planet had essentially grabbed this unwelcome visitor with invisible hands, pulled it apart, and arranged its fragments in an orbital debris train. When scientists calculated the comet's new orbit, they held their breath. The fragments were revolving around Jupiter in an extremely flattened and unstable trajectory. Calculations showed that in the next orbit, the fragments would collide directly with Jupiter's atmosphere. This meant humanity would witness, for the first time, a live collision between 2 solar system bodies. This was not a simulation, nor a tracing of past events. It was happening in real time. Until then, astronomers assumed that craters on planetary surfaces were formed millions of years ago, and that the solar system had settled into calm. Shoemaker-Levy 9 reminded us that the universe is still wild and dangerous. This discovery triggered a near mobilization in the world of astronomy. The most powerful telescopes on Earth and the Hubble Space Telescope in orbit focused on Jupiter. Everyone had a single question in mind: what would this collision look like? Some scientists believed the comet fragments would be silently absorbed by Jupiter's massive atmosphere, leaving no visible trace on Earth. Jupiter was so immense that these ice and rock pieces might vanish like pebbles tossed into an ocean. Others argued that the energy released by the impact would be tremendous and leave lasting marks on the planet's surface. One thing was certain: this rendezvous in July 1994 would fundamentally change our understanding of Jupiter and its role in the solar system. The fragments were hurtling toward Jupiter at an incredible speed of about 60 kilometers per second. This meant the largest fragment would release far more energy on impact than all of Earth's nuclear arsenal combined. Jupiter, as it had done for billions of years, prepared to swallow the approaching object. But this time, we were there. We had secured the front row seat to witness the universe's greatest fireworks show. The countdown began, and the silent giant awaited the approaching storm. When July 1994 arrived, the astronomy world was filled with excitement mixed with deep apprehension. Calculations were confirmed. The fragments of Shoemaker-Levy 9 would strike Jupiter. But there was a problem. This cosmic bombardment would occur on the side of the planet facing away from Earth, hidden from view. Telescopes on Earth had no chance to directly see the initial flash of the impact. Humanity seemed poised to miss the greatest planetary collision in history. Yet luck favored curious minds. In the depths of space, there was a witness at the right place and the right time: the Galileo spacecraft. Galileo had been launched years earlier and was on its long journey toward Jupiter. It had not yet entered orbit, but its position offered an unparalleled perspective. While Earth was blind to the event, Galileo was the only eye witnessing this cosmic spectacle front row. On July 16, the first fragment, named A, plunged into Jupiter's atmosphere at a terrifying speed of approximately 216,000 kilometers per hour, and Galileo was there. The moment of impact lit up the silent void of space like a supernova. Galileo's sensors recorded a sudden temperature spike of 24,000 degrees at the collision point. This was many times hotter than the surface of the Sunday. From Jupiter's dense cloud layers, a colossal fireball and plume of smoke rose, roughly the size of the Australian continent. This was a giant mushroom cloud, or plume, reaching about 3,000 kilometers above the atmosphere. Had this occurred on Earth, it could have torn apart our atmosphere and obliterated life within seconds. But for Jupiter, it was merely the beginning of a long series. Thanks to the planet's rapid rotation around its axis, the disaster unfolding on the far side soon came into view from Earth. Jupiter completes a full rotation every 10 hours. When the Hubble Space Telescope and ground observatories focused on the planet, the sight was staggering. A pitch-black, sooty spot appeared on Jupiter's perfectly colorful bands. This spot was a massive scar on the planet's surface, large enough on its own to engulf Earth. However, the real destruction had not yet run its course. In the following days, the other fragments of the comet continued to strike the planet one by one. Especially on July 18, the fragment known as G delivered the most intense moment of the bombardment. This piece was so massive that the energy released was approximately 600 times greater than the combined power of all nuclear weapons on Earth. The shock waves generated by the explosion propagated through Jupiter's dense atmosphere at hypersonic speeds, rippling the clouds over thousands of kilometers. This was not a simple collision. It was a deep wound inflicted upon the planet's atmosphere. When the impacts concluded, Jupiter was no longer the same. Its southern hemisphere was covered with massive black scars lined side by side. These dark marks were so prominent that even amateur astronomers could observe this cosmic battlefield with small telescopes. Even the famous Great Red Spot appeared pale compared to these fresh, new wounds. Initially, scientists expected these scars to disappear within a few days. However, the marks persisted for months, and in some cases, years, lingering in Jupiter's atmosphere. Yet, this catastrophe proved to be a unique gift for science. The rising plumes of smoke and clouds of debris transported materials from the planet's deep layers normally hidden from view into the stratosphere. When spectrometers analyzed these black scars, they revealed not only the remnants of the comet, but also Jupiter's internal chemistry. Within the debris, heavy elements such as sulfur, carbon disulfide, magnesium, silicon, and iron were detected. Yet the most astonishing discovery was water. In Jupiter's depths, there was far more water vapor than theoretical models had predicted. The comet had carved into Jupiter's surface like a scalpel, exposing secrets hidden at the heart of the planet. This event proved to all of humanity that the solar system is not a static tableau. It is still alive, evolving, and violent. It also posed a chilling question. If Jupiter were not there, who would these rogue celestial objects strike? The dark scars left by shoemaker Levy 9 on Jupiter have etched an indelible mark on humanity's collective memory. The events of those hot summer days in the 1,990 seconds were not just astronomical data, they were a cold wake-up call for our species. The extinction of the dinosaurs, or massive asteroid impacts, were no longer abstract concepts read about in books. Watching Jupiter being pounded made it unmistakably clear that the threat was still real, alive, and right in our cosmic backyard. The sky was no longer merely an innocent void studded with romantic stars. It had become a shooting range filled with rogue minds. This realization mobilized NASA and other space agencies. Today's concept of planetary defense and missions to monitor near-Earth hazardous objects were, in fact, born from the blows Jupiter endured that day. But where does Jupiter stand in this story? Is it the system's brutal enforcer, or a silent guardian protecting us? For many years, scientists described Jupiter as a cosmic vacuum cleaner. Its enormous gravity functions like a massive well, pulling in comets and rogue asteroids coming from the outer solar system. Statistical data support this view. Compared to Earth, Jupiter experiences approximately 2,000 to 8,000 times more cosmic collisions. If Jupiter did not occupy its current position, many of these uncontrolled rocky objects could have been sent hurtling into the inner solar system, into our cosmic neighborhood. This idea forms one of the strongest pillars of the rare Earth hypothesis. According to this hypothesis, the emergence of complex, multicellular life requires planets to maintain relative stability over long periods. If Earth were repeatedly reshaped by massive collisions every few million years, there would never be enough time for life to advance beyond simple, single-celled organisms. For billions of years, Jupiter may have served as a protective shield, enabling the calm evolutionary process that allowed us to exist. Perhaps the very fact that we are here to witness and ponder these words is thanks to this gas giant standing watch. Yet science is rarely entirely black or white. High-resolution computer simulations in recent years have hinted that Jupiter's role may not be entirely benevolent. Yes, it draws in many dangerous celestial bodies, destroying them or ejecting them from the solar system. Yet its immense gravitational pull can also act like a cosmic slingshot, diverting a harmlessly orbiting rock directly toward Earth. From this perspective, Jupiter is both a protective shield and, occasionally, a dangerous neighbor hurling stones at us. Nonetheless, the prevailing scientific consensus today is that the benefits Jupiter provides outweigh the risks it occasionally poses. Now it is time to set aside Jupiter's chaotic and violent nature and turn our attention to the smaller but no less mysterious worlds orbiting it. For Jupiter is not a lone planet drifting through space. It is essentially a miniature solar system. At its center revolves a crowded cosmic family with more than 60 moons. Among them, 4 are particularly special, not mere rocks, but independent worlds with unique geology, character, and secrets. This extraordinary quartet is named the Galilean moons, in honor of the astronomer who first observed them. On one side lies a fiery hell where volcanoes never sleep. On the other, icy shells conceal hidden oceans that may harbor life. These moons are cosmic masterpieces, surviving and constantly evolving under Jupiter's overwhelming gravitational grip. Leaving behind the storms in the giant planet's atmosphere and its cosmic impacts, we now turn our course to these fascinating moons. Our first stop is Io, the most restless, explosive, and hellish world in the solar system. Orbiting just beyond Jupiter's deadly radiation belts, Io is one of the most unfortunate, yet simultaneously impressive, of the Galilean moons. It is the closest of the Galilean moons to Jupiter. Were you to stand on its surface and gaze at the sky, you would be confronted with a mind-bending spectacle. Jupiter would dominate the horizon, spanning 39 times wider than the moon as seen from Earth. This view is so imposing that the concept of night on Io is illuminated by the faint light reflected from Jupiter itself. Yet such proximity comes at a terrifying cost. Io is not merely a loyal moon of Jupiter, it is a captive of the giant's gravity. Unlike Earth's moon, which takes roughly a month to orbit our planet, Io completes a full orbit around Jupiter in an astonishingly short 42.5 hours. This extreme speed and proximity make free rotation around its axis impossible. Like the moon showing the same face to Earth, Io is gravitationally locked, forever presenting one side to the gas giant while the other faces the dark, cold void of space. Io's tragedy is not confined to this relationship with Jupiter alone. Its complex cosmic dance with Europa and Ganymede determines its ultimate fate. These three moons are locked in a precise mathematical rhythm. While Ganymede completes one orbit, Europa completes two, and Io completes four. This resonance causes the moons to approach each other at regular intervals, exerting gravitational pulls. While Jupiter's immense gravity tugs Io inward, the weaker but rhythmic pull of its outer siblings stretches it outward. Io is caught in the middle of a cosmic tug-of-war. Throughout this process, Io's orbit is continuously compressed, stretched, and twisted. A comparison to Earth's tidal effects can be made, but Io's experience far exceeds it. On Earth, the moon raises ocean tides by a few meters, whereas Jupiter's influence on Io is so intense that even its solid rock surface rises and falls by about 100 meters. The ground beneath your feet swells and sinks daily to the height of a skyscraper. This constant mechanical strain generates tremendous friction within Io's interior. If you bend a metal wire repeatedly, you feel it heat up. Io has been warming similarly for billions of years under Jupiter's relentless pull. This mechanical energy transforms into intense heat deep within the moon. Despite being far from the sun, Io should be a frozen ice ball, yet it burns from the inside, while Jupiter's other major moons are icy and water-rich. Io has become a completely dry, dense sphere of rock and metal due to this internal torture. This heating makes Io the geologically most active body in the solar system. Because Jupiter rotates around its axis at an extraordinary speed, its enormous magnetic field is dragged along with the planet. This magnetic field moves through space far faster than Io's orbital velocity. Magnetic waves passing through Io's thin atmosphere and its dense cloud of ejected plasma generate a powerful electric current. But this is no simple static electricity. Between Io and Jupiter flows a massive electric river, reaching millions of amperes. This invisible connection, called the flux tube, acts like an umbilical cord, continuously transporting energy between the planet and its moon. The energy flowing through this tube is so intense that it produces a potential difference of approximately 400,000 volts. No power station built by humanity can compare to this wild and uncontrolled natural electricity. During its mission, the Juno spacecraft dared to pass through this flux tube and miraculously survived, mapping the invisible force in detail. When this electric current reaches Jupiter's poles, it transforms into a dazzling display. At the point where the flux tube plunges into the planet's atmosphere, gases are intensely heated and excited, producing the continuously glowing auroras at Jupiter's north and south poles. While auroras on Earth are largely tied to solar storms and fade with time, Jupiter's auroras carry Io's signature. This luminous mark follows the Moon as it orbits, tracing its path across the planet's poles. The phenomenon of a moon leaving a light imprint on its parent planet's atmosphere is among the most mesmerizing interactions in the universe. Yet this impressive relationship has a dark side. The plasma torus and flux tube transform Jupiter's surroundings into an extremely hazardous radiation hell. This region is filled with radiation intense enough to immediately disable electronic systems and eradicate any biological life within minutes. Io is not only dangerous due to its constantly erupting volcanoes, but also because of the lethal energy it emits into space. A realm where fire, sulfur, and electricity intertwine, a world completely devoid of life, yet possessing a wild and savage beauty. Now we leave this chaotic world of fire and radiation behind. As our journey around Jupiter continues, the scenery will dramatically change. Fire will give way to ice, sulfur will give way to water, and chaos will be replaced by profound silence. If Io is hellish and violent, the next stop promises hope and calm. Moving outward in Jupiter's orbit, leaving Io's flaming surface and sulfuric atmosphere behind, we encounter a world dominated not by fire, but by ice, Europa. One of the brightest moons of the solar system, Europa shines in the dark void like a flawless pearl. Despite Jupiter's crushing gravity and deadly radiation, it presents a serene, smooth, and mysterious beauty. Scientists have dubbed it the Icy Kingdom, making it one of the most intriguing stops in our exploration of the system. As we approach Europa, the first striking feature is its extraordinary brightness. Its icy shell reflects the faint sunlight so powerfully that from Earth it appears about 5 times brighter than the Moon. However, this dazzling brightness signals extreme cold. At the equator, temperatures drop to -160 degrees Celsius, while at the poles, they reach -220 degrees Celsius. Under these conditions, the ice does not behave like ordinary frozen water. It becomes as hard as granite, as durable as concrete. Europa's outer shell is made of this nearly impenetrable ice armor. A closer examination of the surface reveals another feature that surprises scientists: smoothness. Unlike many solid bodies in the solar system, especially its neighbor Callisto with its dense craters, Europa's surface shows very few impact marks. On a celestial body that has been bombarded by meteors for billions of years, The near absence of craters is an important clue. The surface is young. Estimates suggest Europa's icy crust is only 20 to 80 million years old. That is, like Io, this moon is a living world that constantly renews itself. However, Europa accomplishes this not with lava, but with the movement of ice and water. This white, smooth surface is covered with massive cracks called linea. From a distance, these resemble a cracked eggshell or the veins across a giant eye. Stretching thousands of kilometers, these intersecting fractures form a complex network on the surface, which contrasts with the surrounding white ice in shades of reddish-brown and tan. Scientists believe these colors result from salty water and sulfur compounds from below, interacting with intense radiation at the surface. But who or what cracks this ice as hard as granite? The answer is hidden in Jupiter's invisible but powerful hands. Like Io, Europa is subject to Jupiter's immense gravitational pull and the orbital resonance with other moons. However, being farther away than Io, it does not transform into a molten volcanic world. Instead, Jupiter's tidal forces continuously stretch and flex Europa's icy shell. As the moon approaches and recedes from the planet along its orbit, this ice shell cannot withstand the increasing pressure and cracks. Through these fractures, warmer, softer ice, or possibly liquid water, rises, fills the crack, and refreezes. This process is like a wound healing on a cosmic timescale over millions of years. The surface features not only include long cracks, but also lenticulae, or commonly called red spots, and chaotic terrains. Chaotic terrains are regions where the ice has fractured, shifted, and refrozen like a giant puzzle. These formations provide the clearest evidence of movement beneath the ice shell. Rising warm currents cause the ice to melt or soften, and ice blocks shift and refreeze, forming these complex patterns. All these cracks, lines, and chaotic regions scream one truth. Beneath this hard, cold, seemingly lifeless shell lies a dynamic, flowing world. The fractures are not just traces, but an invitation from below, because beneath this thick ice armor, one of the solar system's greatest secrets may be hidden: a vast ocean capable of hosting extraterrestrial life. Leaving Europa's icy kingdom behind, on the horizon the system's true giant slowly emerges. Larger than Mercury, possessing its own magnetic shield, and called the King of Moons, our next stop comes into view: Ganymede. Sliding past Europa's smooth, gleaming ice plains toward the outer reaches of Jupiter's system, the scene before us is literally breathtaking. Now appears a world for which calling it just a moon would be an understatement: Ganymede. This is not only Jupiter's largest moon, but the largest natural satellite in the entire solar system. Its size is so vast that it even surpasses Mercury, the closest planet to the Sunday. If Ganymede orbited the Sun directly instead of Jupiter, we would classify it as a planet without hesitation. With a diameter of 5,268 kilometers, this giant is larger than Pluto, the Moon, and even Mercury. Yet this impressive size is misleading. Its mass is less than half of Mercury's because its composition is not dominated by dense metals and rock like Mercury, but largely by water, ice, and silicates. Ganymede is roughly half rock, half ice, a colossal sphere. Its name comes from mythology. honoring the young cupbearer of the gods, and it deserves this title due to the enormous water reserves it holds. So much so that it is believed to contain more water than all the oceans on Earth combined. However, what makes Ganymede legendary in the scientific world is neither its size nor its water content. The real turning point came in 1996, when the Galileo spacecraft passed close to Ganymede. Its sensors recorded an unusual signal, almost like a magnetic whistle. Upon examining the data, scientists could hardly believe their eyes. Ganymede has its own magnetic field. This discovery made it the only known moon in the solar system with its own magnetic field. Normally, magnetic fields are exclusive to planets with molten and rotating metal cores, like Earth or Jupiter. The fact that a frozen moon could generate a magnetic field strong enough to affect a compass was previously thought impossible. This field shows that Ganymede forms a small magnetic bubble within Jupiter's massive magnetosphere, like opening an umbrella under a deadly rainstorm. The presence of this field also proves that Ganymede's interior is not entirely frozen. Deep inside, a liquid, moving iron core spins, acting as a dynamo and spreading invisible magnetic lines into space. One of the most striking proofs of this field is the auroras observed at Ganymede's poles. Like on Earth and Jupiter, this moon has its own northern and southern lights. Hubble directly observed these auroras in its thin atmosphere. However, these auroras do not drift freely like on Earth. Ganymede's magnetic field is embedded within Jupiter's overpowering magnetic strength. Thus, its auroras swing back and forth like a cradle in response to Jupiter's field changes. Scientists use this motion to infer Ganymede's interior, especially the subsurface ocean. Ganymede's atmosphere is as fascinating as its magnetic field. Despite being extremely thin, it contains oxygen. However, this is not breathable air. The pressure is billions of times lower than on Earth. The oxygen forms when water ice on the surface is split by radiation. Lighter hydrogen escapes into space, while heavier oxygen atoms linger near the surface. Technically, Ganymede has an oxygen-containing atmosphere, a magnetic shield, and massive dimensions like a rough draft of a habitable planet. Now we prepare to descend beneath this magnetic giant's surface into the depths of its ice-covered shell. Ganymede's true secret lies not only in its core, but in the layered structure of ice and water inside. Scientists call this the cosmic sandwich, which could completely change what we know about ocean worlds. For many years, scientists thought this giant moon consisted of a single ice shell with a single underlying ocean, like Europa. However, Ganymede is so massive that its gravity allows a more complex internal structure than the usual ocean model. Here, water and ice layers may stack atop each other, forming multiple alternating layers. At the bottom, the saltiest and densest water layer may come into direct contact with the rocky core. If this scenario is correct, chemical reactions capable of supporting life may also occur deep inside Ganymede, just like on Europa. Ganymede's enormous water body and core remain warm despite being far from the sunday. Unlike Europa and Io, Jupiter's direct gravitational effect is weaker here. But Ganymede is not alone. Its siblings maintain a cosmic resonance that provides the main source of this energy. Io, Europa, and Ganymede are locked together like a celestial clock. When Ganymede completes one orbit around Jupiter, Europa completes 2, and Io completes 4. This mathematical arrangement causes moons to pull on each other periodically, slightly elongating their orbits. Ganymede experiences constant stress along its orbit, sometimes approaching Jupiter, sometimes receding. Imagine squeezing a hard rubber ball repeatedly. Eventually, you can feel it warm up. For billions of years, Ganymede has been squeezed and released by these invisible forces. The resulting tidal heating is not enough to trigger volcanic eruptions like Io's, but keeps Ganymede's core liquid and its oceans from freezing in space's extreme cold. This internal heat also shapes the surface, creating a strange collage of the solar system's oldest and newest formations. On one side lie dark craters billions of years old. On the other, brighter, younger ice streaks cut through them. These surface features silently record Ganymede's geological past, periods of crustal fracture and refreezing. Now, we make an imaginary landing on this moon's surface. Under our feet stretches a landscape that whispers Ganymede's turbulent history. Unlike Europa's smooth ice plains, this surface is extremely rugged, complex, and fragmented. The surface of the moon resembles a gigantic patchwork quilt, as if two different worlds, two separate eras, had been stitched together. On one side lie dark regions, carrying the weight of billions of years, and on the other, bright and sharply defined valleys reflect the energy of geological youth. Covering roughly 1/3 of Ganymede's surface, these dark areas preserve the oldest memories of the moon. They are dotted with countless craters, remnants of the intense bombardment during the early solar system. These dark regions are known as Galileo Regio, and, with their nearly untouched circular craters, resemble a cosmic museum. Here, time seems frozen billions of years ago. There is no wind, no rain, only endless silence and the pits carved by falling space rocks. Yet slicing through these dark zones are bright streaks, sharp and clear, like a blade has passed over them, revealing the other side of the story. These lighter regions, which make up the rest of the surface, are called grooved terrains. This is no flat ice plain. It is a complex labyrinth of steep ice mountains, rising up to 700 meters, and deep valleys stretching for kilometers. The formations resemble rows of massive railroad tracks laid side by side, or the furrows of a meticulously plowed field. Who, then, raised the mountains and carved the valleys in this frozen world? The answer lies again in an invisible yet powerful force: tidal stress. In Ganymede's past, orbital variations created periods of much higher internal heat. During these times, Jupiter's gravity stretched and strained the moon's crust relentlessly. Just as continents drift apart on Earth, Ganymede's ancient, dark crust could not withstand this tension and fractured. From the broken crust, cleaner, brighter water or softer ice from the depths surged upward, filling the gaps and freezing. But this was not a one-time event. The crust cracked repeatedly, faults overlapped, and ice blocks shifted and collided, forming the massive mountain ranges and grooves we see today. The bright streaks on the surface are, therefore, scars of Ganymede's crust tearing and healing over time. These features provide clear evidence of the moon's once intense tectonic activity. The bright fault lines cutting across the ancient dark craters show that Ganymede has expanded over time, as if the moon swelled from internal pressure and its old crust could no longer contain it. This geological diversity sets Ganymede apart from other moons in the system. It is neither entirely dead like Callisto, nor completely volcanic like Io. It occupies a unique middle ground, a world where icy mountains, deep oceans, magnetic fields, and ancient craters coexist. Leaving behind Ganymede's complex and active geology, magnetic shield, and hidden oceans, we drift further from Jupiter toward the outermost edge of the system, where solitude is most deeply felt. There, waiting in quiet majesty, is a silent giant, untouched by the frenzied dance of its siblings, with no volcanoes or towering mountains. We approach the orbit of Callisto, known as the Dead World, bearing the oldest and most battered surface in the solar system, preparing to listen to the silence. Sometimes, the greatest secrets are hidden in the faces of those who never speak. Every storm system on the planet is a reflection of the energy generated within and the complex fluid dynamics at play. Jupiter's atmosphere is not just a layer of gas. It is a colossal energy furnace extending millions of kilometers deep. Hot gases rise while colder gases sink, creating a continuous cycle of transformation. Thanks to Juno's measurements, scientists realize that the polar storms are not merely surface features, but are fed by deep, interconnected fluid root systems, colossal structures hidden from plain sight. Beneath Jupiter's massive gas layers lies the true mystery, the planet's core. No matter how turbulent the clouds, storms, or colorful bands appear on the surface, the real power comes from the dense, likely metallic hydrogen layer at the center. This core functions as a giant dynamo, generating Jupiter's enormous magnetic field. Juno's magnetometer mapped this field in 3 dimensions, revealing its intensity at every point and offering unique insights into the planet's interior. The white and red bands observed in Jupiter's clouds are massive currents of gas with different temperatures and chemical compositions. Components such as ammonia, water ice, and methane interact with rising hot gases, creating the iconic colored bands we see on the surface. These bands are like veins through which the planet's internal heat and energy flow, narrating the story of its dynamic interior. The geometric storm patterns at Jupiter's poles are mesmerizing. The northern octagon and the southern pentagon indicate a steady rhythm in the planet's internal energy and fluid dynamics. It is as if Jupiter orchestrates chaos on the surface while binding it to an underlying mathematical order. Storms collide without merging and drift apart without breaking, challenging scientists to rethink the limits of fluid dynamics and planetary science. With Juno's infrared eyes using the GIRAM instrument, scientists observed that storms are not confined to the surface. They are continuously fed by deep energy sources. The contrast between hot areas in lower layers and cold regions atop cloud peaks maps the planet's colossal energy furnace in detail. Each orbit, Juno updates this map, gathering new data and gradually unraveling Jupiter's dynamic structure. In short, Jupiter is not merely a gas giant, but a living system, displaying one of the universe's most captivating shows of energy and motion. Beneath its clouds, churning fluid flows, a heart powering the magnetic field, and perfectly geometrical polar patterns reveal the hidden complexity of the planet. Yet one of Juno's greatest surprises came from its microwave radiometer, designed to probe even deeper layers of the atmosphere. For years, scientists assumed Jupiter's gases were uniformly mixed beneath the clouds. That is, ammonia, water, and other gases were thought to be evenly distributed. Juno's microwave scans shattered this assumption. Contrary to expectations, Jupiter's atmosphere is extremely irregular and complex. In particular, a dense column of ammonia was detected plunging deep in the equatorial region, extending about 350 kilometers below the clouds. In other latitudes, ammonia levels were surprisingly low. This revealed a massive atmospheric circulation system unlike any on Earth. The ammonia-rich equator and depleted surrounding areas indicate a vast global meteorological phenomenon, operating on a scale far larger than terrestrial weather. These findings overturned the old view of Jupiter as a simple gas ball. The planet is like a massive onion with distinct layers, each following its own chemical and physical rules. Moreover, these layers are not static, they move constantly. Juno's measurements of deeper layers show that the famous colorful cloud bands are not mere surface paint. The wind belts extend thousands of kilometers into the interior. As colorful and dynamic as Jupiter's exterior is, its interior is equally filled with deep, mysterious flows. Juno's discoveries have rewritten our understanding of how gas giants operate. Yet the spacecraft's primary mission is to map the planet's invisible shield, the magnetic field. During this mapping, a previously unseen structure, potentially rivaling the Great Red Spot, was discovered, the Great Blue Spot. We now enter the invisible world of magnetic fields, trying to decode the anomaly created by the metallic ocean in Jupiter's core. Beneath the mesmerizing colored clouds and storms lies another structure, invisible to the eye, but representing the planet's true power, its magnetic field. This field envelops the planet like a massive protective shield. Juno, using its rotating structure and onboard magnetometers like a lighthouse, mapped this invisible force, revealing an unprecedented and puzzling Jupiter. Expectations of a regular magnetic field with clear north and south poles were defied. Instead, Jupiter's magnetic field is patchy, irregular, and full of surprises. The most remarkable of these surprises is the region coded in blue on the maps and called the Great Blue Spot. This is not a storm or cloud visible to the eye, but a magnetic anomaly. Near the equator, magnetic field lines concentrate and strengthen inexplicably, as if a gigantic hidden magnet lies just below the surface. The Great Blue Spot alone is many times stronger than the Earth's total magnetic field. This invisible spot is proof not only of the planet's surface complexity, but also of its intricate internal structure. Juno's precise measurements revealed that the magnetic field changes over time, a phenomenon known as secular variation, showing that Jupiter's magnetic map is not static, but slowly drifts over the years. The driving force behind this shift is the deep atmospheric winds. Juno detected that the Great Blue Spot was being pushed and pulled by the intense winds deep within the planet, as if it were being dragged along. This finding was revolutionary for the scientific community, because for the first time, we were seeing that a planet's atmospheric winds could physically influence its magnetic field. This discovery opened a new window into understanding the dynamic interactions between a planet's atmosphere and its invisible magnetic shield. It also led us to answer one of Jupiter's greatest mysteries. How deep do those famous colored bands and storms actually go? For years, these stripes were thought to be shallow meteorological phenomena confined to the upper layers of the atmosphere. But Juno's gravity and magnetic data proved that the reality is far more profound. The iconic winds of Jupiter extend downward from the cloud tops for a staggering 3,000 kilometers, roughly half the distance from the Earth's surface to its center. This means that Jupiter's atmosphere is not a thin shell, but a vast, moving ocean that accounts for about 1% of the planet's total mass. This 3,000-kilometer depth represents a critical threshold for the planet's dynamics. Below this point, pressure and temperature rise to such extremes that hydrogen no longer behaves as a simple gas. Here, matter transforms into an exotic, electrically conductive liquid, and the rule of atmospheric winds ceases. The turbulent upper gas layer flows over this denser, more inert liquid beneath. Jupiter's atmosphere extends its roots downward until slowed by the magnetic braking effect from below, intertwining wind and magnetism in an intricate dance. Juno's observations also helped us understand the roots of the Great Red Spot. This colossal storm is not merely a floating raft on the surface. It plunges at least 350 kilometers deep, possibly even further, with its base hotter than its peak. This heat difference fuels the storm's engine, powering its rotation for centuries, making it one of the most enduring phenomena in the solar system. Viewed through Juno's eyes, Jupiter is no longer just a beautiful gas giant. It is a complex machine where enormous energy and material exchange occurs between layers. Winds bend magnetic fields, and storms anchor their roots into deep oceans. Yet the most mysterious part of this machine lies in the darkness, where the winds cease and the strange, metallic matter begins. Now we prepare to dive into the metallic ocean at the heart of the planet, where hydrogen turns into metal, pushing the boundaries of known physics. This is the final destination of our journey, Jupiter's metallic core. This immense sphere of gas, surrounded by its crowded family of moons, has been silently performing a cosmic waltz in the dark suburbs of the solar system for billions of years. Thanks to Juno's daring dives, we now know that beneath Jupiter's colorful and turbulent clouds lies a world that defies our imagination. Here, winds slam into metal, rains may consist of diamond or helium, and storms rage uninterrupted for centuries. This place is proof of how wild nature can be, yet simultaneously governed by an almost mathematical order. From our safe blue planet, millions of kilometers away, we observe this giant, and in doing so, glimpse our own past and the chaotic birth pangs of the solar system. Jupiter, with its mass, acts as a protective shield, a teacher whose secrets draw us in, and a silent guardian reminding us of our place in the cosmos. Now, allow these immense images, the red storms and the icy plains, to slowly fade from your mind. Juno's engines are silent, Galileo's data has been archived, and telescope lenses are closed. The era of scientific probing, complex data, and cosmic mysteries gives way to the profound and healing silence of space. Imagine Jupiter's immense gravity, slowly drawing away all your exhausting thoughts, the weight and chaos of the day. Just as it swallows stray comets, it pulls the noise of your mind into its deep interior, leaving calm and clarity behind. Feel yourself drifting along Jupiter's orbit, like a weightless speck of dust in the infinite void. Around you is only the faint light of distant stars and the darkness as vast as space itself. Neither the searing heat of Io nor the freezing cold of Europa can reach you now. There is only peace, only serenity, and an endless flow. As Jupiter's massive body continues its slow rotation in the darkness, you synchronize with its calm rhythm. With every breath, you sink deeper into the universe, becoming lighter and more suspended in space. Your eyelids close with the soothing weight of Jupiter's gravity, heavy yet comforting. The long voyage along the frontier of the unknown has ended. Now is the time not to ask questions, but to rest in the silence of answers. As the stars take watch, you glide toward a safe, warm, and deep darkness, the threshold where dreams begin. In this quiet corner of the cosmos, everything is as it should be. Good night.